Hey everybody, today we'll do another quick video, and today I will do a video in finding still in circuits, AC circuit, but it's going to be in the find the impedance when the values of the capacitance and inductors are given. In this case, I will do a little two problems real quick here. And in this right here, I want it before I start because it seemed like so the answer for that is this one, which is 50 negative J 26. Hold on. This doesn't look too good. So it's negative J. Right here, this is negative. So it's negative 26 5 25 ohms. Right? This is the answer. It's not clear here, but that's technically supposed to be. So basically, we will work these problems out, and hopefully we come up with those numbers, right? Okay, so the first problem says determine the equivalent impedance of the circuit below when we assume that the frequency is 60 hertz, right? So, and then we will do this problem. It's the same thing, it's just with a different configuration and extra piece of information here. Kind of the same thing. Over here we have a capacitor in a resistor, or here we have a resistor and an inductor. So, but I will show you guys how to do that. So, let me draw the first one. The first one we have something like this, right? So we have something like this, and then we have a capacitor, right? And the capacitor, it doesn't matter where location is located. That doesn't matter as long as it's in series, right, or in parallel. I mean, not gonna make a difference. Now, so here we will have that. We have a capacitor, and then we have an resistor, and that resistor is indeed in series, and we find in C. We find the C value, right? In the capacitor is 50 ohms. I'm sorry, the resistor is 50 ohm. The capacitor here is 100. It's 100 nanofarads, right? So we will have we need a formula. In this case, we cannot just do the J. We don't have the J formula, right? So we have to convert this into a J. And how we do that? Well, how we do it, we have to find what is called capacitive reactance of the capacitor, which is basically the same as saying resistance or impedance, right? Impedance of the capacitor. And by doing that, we do it this way. To do that, I would say we do it this way. We say that XC, right? This is the inductive reactance of the the capacitive reactance of the capacitor is going to be equal to 1, right? It's going to 1 is going to be equal to 1 over J omega omega z, right? When omega z, and let me just write this down. When omega c, right? So omega c is omega is the frequency and z is the capacitance, but omega has a value of omega, and sometimes when we do the omega z, right, sometimes the books do it like this, right, with the little c, omega z, right, which it says that this is a capacitance. Yeah, this is a frequency related to a capacitor, right? So now what we do right here, we say that 1, right, over j, right? In this case, it's going to be equal to, well, we know that that is that, right? All we have to do right here is simply do it this way. So we do 2 pi f, which is a frequency, times, right? Times what is what? Times z, right? So basically, omega is equal to this piece right here and multiplying by the z value. So in other words, we will have that the xc is equal to 1 over the frequency, and the frequency is 60 hertz, right? So we do 2 pi, and then we do times, right? Times 60 hertz, right? And then times 100 times 10 to the minus 9. And why to the minus 9? Because that is a nano value, right? So basically, we do that. When we do this math, we get that the bottom number is going to be equal to 2 pi times 60 times 100, 10 to the minus 9, and we get a number that is a very small, right? Of course it's going to be a small, right? Because we got a nano over there. So what we have is that this value right here, we got xc is equal to 1 over 0.0033769, right? Okay, so we take that number, right? We take 1 and we divide it by that number. Okay? And we get a value for xc, right? Remember, we have to attach this. And also, we have to remember that this capacitor is 90 degrees negative. I will say, well, I don't want to confuse anybody. When I say 90 degrees, I mean down, right? 90 degrees down. But to be more clear, is 270 degrees in the unit circle, right? So in other words, the capacitor is down. Therefore, we're going in the negative J, right? Remember that we're dealing with imaginary, but electrical engineers, we don't use the I, we use the J. So therefore, in this case, I have to attach that J, right? And that is going to give me a negative number, which is technically that value is going to be a negative and it's going to be indeed 26 5 2 5, and this is a J. Okay, so if I can undo the last, okay, and this is a J, and this is of course ohms, right? So the answer, the C value for this is nothing but 50, because 50, the 50 ohms, that 50 ohms right there is in series, right? So now that is going to be equal to 50 in series with a minus, with a negative J, right? Which is the capacitor capacitance reactance, which is J 26525 ohms, right? So that is right. Okay, so that's it for the first one. Okay, so let's do the next one. In the next one, we have a capacitor in parallel with that resistor and that inductor, right? The only difference that we have an inductor here, and it's in parallel with this capacitor, and this capacitor is in series. I'm sorry, this inductor is in series with this resistor, right? So now, because this is a little different, do you think that it's fair to say that the Z value is equal to parenthesis R, right? The resistance plus something which is an inductor. Remember, now the inductor is 90 degree up, right? Inductance is 90 degree up. So we can say that inductance has a value of a positive value, right? So now we do it just J, and that is going to be a J, right? J, and it's going to be XL. Why XL? Well, because it is that inductance reactance of the inductor, right? And then that is in parallel with what? With the J, the capacitor with a JXZ, right? I think we can say that, right? Now let's do the mathematics real quick for that one. In that one, I think the value for that one, the only thing different is a nano instead of it is a nanofarad, and we have a 2 millihenries inductor, right? So we have a 2 millihenry inductor in series with the resistor of 10 ohms. So let's do it. So right here we do, right? And then we come over here down and add that capacitor, right? Right? And then we do in parallel, we add a resistor to it, and then also in parallel we add an inductor, right? And then we bring that, right? So now this inductor right here, we find Z again, right? That's what we're trying to find. And that inductor right here is 2 milli and Henry, and then we have a 10 ohms, and then we have here what we have 100, so we have 100 We have 100, and it's micro. Micro is like this with a mute. It's called a mute, which is nothing but 10 to the minus 6, right? And this is farads. Okay, so we have 10 microfarads capacitor, right? And we have this resistor, and we have this millihenry. The capacitor values are usually smaller, right? The capacitor values are usually smaller, right? Now, let's do this. Okay, so we have that. Now, let's do this. So here, what I can do, we can do this step by step again, so we can find xz, which is equal to 1 over, right? We know that 2 pi f times 2 pi f, right? Frequency is 60, right? You multiply by 2 pi is equal to 277, right? It's equal to about 277. So, I'm sorry, 377, right? So, if you take 2 pi, and you multiply that by 60 hertz, right? It's about 377, right? Now, and remember that this is omega. Omega is technically 2 pi f, right? Now, that is multiplied by the Z value, which is the capacitor value, which in this case is times 100 times 10 to the minus 6, which is equal to, in this case, is going to be equal to times 10 to the minus 6, right? And we take that number, 1 divided by that number is going to be equal to, let's see. Okay, hold on. Let's see. It's a micro. It's 100 micro. So yeah, so here, what we do is 377 times 100 times 10 to the minus 6. Okay, and that is equal to 1 over 0.00377, which is equal to 26.5, 26, which is equal to 26.5, right? And that is indeed ohms, which in reality this is J, negative J, 26.5 ohms, right? And why? Because we're dealing with a capacitor, right? So we have that value, right? We have that. Now let's do this. Let's do this too, guys, right here. So now we use the formula that is called it's called XL. Why XL? Because it's the L is the inductive reactance, right? So now we do okay, let me just do it this way. So, okay, so it's going to be omega L, right? Omega L. And why? Well, and then we say that why omega L? Well, omega is nothing but 2 pi f, right? And L is nothing but, in this case, L is nothing but 2 millihenries, right? Now, when we replace those values, we get XL is equal to 2 pi times, right? Times 60 times 2 times 10 to the minus 3. Why to the minus 3? Because we have millihenries, and millihenry is indeed 10 to the minus 3, right? In scientific notation, right? Now, so let's do this again, right? Let's do this mathematically real quick. And we get that 2 pi, right? And then we do times 60 times 2 times 10 to the minus 3, and we get that indeed this number of, and also remember right here, oops, remember we dealing right here, this indeed should be j omega L, right? So in this case, we will have a value of XL is equal to J 0.75, right? Now, what will be the final answer, right? We say that the resistor was going to be in series with this guy, right? So the resistor is in series, so therefore our answer should be the Z C is equal to 10, right? The value of the resistor plus, right? Plus 0.75, right? Actually, it doesn't look too good right here. So okay, so we can do plus J 0.075, right? And then that is going to be in parallel with the value of the capacitor that in our case was negative J 2660, 26.5, I think. 26.5, and everything right here is in ohms. So that will be the answer. For that, right? Okay, so that would be the answer for that. So technically, that is the two, answer for those two problems. And again, thank you for watching. Remember that we actually learned something over here in the Conservative Engineering Academy because Jesus is good, right? Jesus is awesome. And Jesus is the Lord. And Jesus is our Savior, right? Now, take care. And I see you in the next video. Thank you for watching.